It's 31st. We're live. Hello, world. My name is Alan. We're practicing lit code live. It's 31st October. I have my blue pen. I have my black pen. So, notebook ready. And let's see what the problem we have to practice for today. So this is the problem we solved yesterday. What a ride it was. And that's the, okay, we have the last one in the heap priority queue category. Let's see what it looks like. Wow. Wow. How about that? So yesterday's problem, just to give you, I had to use the package heap from Go's standard library. Otherwise, it just wouldn't run within the time limit. But look at this code. Obviously, you would, on an interview, you would probably just do, I don't know, this, maybe there's just high level. Yeah, you might just use the high level without all that. So I don't know if you can even remember that you need to do this, and then you need to initialize it, and then you can use the push, and then you can use the pop, and actually this push and pop, they have their signatures are. So it's not really an interview. Well, the way it's implemented in Go, I don't think it looks the heap looks very interview format. So now that was the problem description of this size. Now the next problem that we're going to do today, let's start the clock. And we want to stay within the hour, okay, for this one, because yesterday took me so much longer. I was trying to do something without using the heap. So, and now this description is quite lengthy, but let's see. It's about workers, about hire, and the cost of hire. Now let's see if we can even understand it within the first 10-15 minutes. So you are given zero index integer costs, where cost is the cost of hire, the ith worker. You are also given two integers, k and candidates. We want to hire exactly k workers according to the following rules. Okay, that sounds interesting because I've been in recruiting for a while in my first career, so I understand what means candidates, and if we need k hires, they will need much more candidates. In each hiring session, choose the worker with the lowest cost from either the first candidates. Now it starts getting tricky. Okay, there are hiring sessions. For the ith worker. Is the cost of hiring ith worker. I don't know if this is interview format. because check this out. You need to read like a full page of text just to get the description of the problem and its examples. 2 examples, yeah. Okay. Let me just read it to myself first. This is like this first sentence is already like, it was good about candidates and hires until that. But since, yeah, from this line, it starts getting completely. For example, if costs and candidates too, then in the first hiring session, we will choose the 4th worker because they have the lowest cost. In the first hiring session. In the second hiring session, candidates too. And we will choose. I don't understand what's the hiring cost. Who are these ith worker? Okay, I is the worker, and K is the number of hires. Worker. Okay, in the second hiring session, we will choose first worker. This problem is already like a challenge just to understand it. We will choose first worker because they have the same lowest cost as 4th worker, but they have the smallest index. Okay. Please note that the indexing may be changed in the process. I'm noticing that. Is there, and that sounds like you might need to implement a queue. Depends on the constraints. Yeah, the length is 10 to 5, cost is 10 to 5. Length is 10 to 5. In this, please know, okay, if there are fewer than candidates, if there are fewer than candidates, workers remaining, this is lit code 75. Okay, so you know. Choose the worker. I mean, you really need to like having like pages of explanations. It might be actually much simpler than this laundry list of bullet points. Laundry list of conditions and rules, and if there are fewer than candidates, workers remaining, if workers remaining, if there are fewer than candidates, choose the worker with the lowest cost among them, break the tie by the smallest index. A worker can only be chosen once. Turn the total cost to hire exactly key workers. So workers. Okay, these are costs. I am kind of confused because we have the term worker, have the term hire. K is hire, and then we candidates. We need to make K workers, hire 2 workers. Yeah, so okay, let's look at an example. Candidates, 3 hires, 4 candidates. Yeah, an example might help. I'm ready to pull out my red pencil. Seriously. When I see when I see a description of that length, yeah, I might need to use my ruler, my measuring tape, to measure how long this description is, my IKEA measuring tape. Yeah, because this is like forever. This description. Yeah, so okay. Example. My example. We have the costs. Okay, there's about 10 or something. We need to make 3 hires. And what is 4 candidates? What is 4 candidates? We'll see. We hire 3 workers in total. Now, that I understand. Okay. The total cost is initially 0. Makes sense. In the first hiring round, we choose the worker from and then these are underlined. 7 is not underlined. The lowest cost is 2. What is that? I mean, why is it underlined or not? Hiring sessions. You will run K sessions and hire exactly 1 worker in each session. K sessions. In the first hiring round, we choose the worker from. The lowest cost is 2, and we break the tie by the smallest index, which is 3. 1, 2, 3. The total cost is 0 plus 2. In the second hiring round, which is the worker from 4, 1, 2, 3, 4. The lowest cost is 2, index 4. Total cost is 4. In the third hiring round, which is the worker from the lowest cost is 7. Index 3, 1, 2, 3. The total cost. Notice that the worker with index 3 was common in the first and last 4 workers. Total hiring cost is 11. Okay, I get the basic math. I'm trying to understand these batches, these candidates, 4 candidates. How does that work? What's the rule here? One worker in each session. In each choose the worker with the lowest cost from either the first candidates workers or the last candidates workers. Oh, okay. That's why these first 2 or last 2. I don't know how that applies to real life, but essentially they're saying, okay, you can choose from the first the length of this number, first 2 or last 2. In this case, it's just first 2, yeah, or last. Okay, we have 3 hires, 3 candidates. We hire 3 workers in total. The total cost is initially 0. Okay. In the first hiring round, we choose the worker from either this or that. The lowest cost is 1, and we break the tie by the smallest index, which is 0. The total cost is, notice that workers with index 1 and 2 are common, the first and last 3 workers. Yeah, these ones. In the second hiring round, we choose the worker from these 3. The lowest cost is 1, 2, 3. Is 1. The third hiring round, there are less than 3 candidates, which is the worker from the remaining candidates. The lowest cost is 2. Okay, so the total cost is plus 2 plus 2 is 4. The total hiring cost is 4. So that's kind of the rules. These are the rules. I'm a bit rusty, but 15 minutes just to read all this stuff. Am I a slow reader? Maybe. I'm still recovering. Yeah. What do we have here? We have a list which could be long as 10, 5. The costs, but it's at least 1. Okay, and candidates is up to that length. Costs are also up 10 to 5. And the logic is, yeah, we need to do this k number of operations, k number of readings of these batches. this bench of candidates, bench of workers. Yeah, so we get two benches in the beginning and in the end, and obviously, and that's all we get essentially. So it's like, and once we get the hire, we just remove that candidate. But. So, the problem here, what is the problem? Yeah, we would read, yeah, in the beginning, like, let's read these four. Then we'll read in the end, pick the minimum. Pick the minimum. And remove it. Yeah, we also need to consider the index. So we want to first start from no, we do need to remember their indices. So we do need to check all of them, and only if there is a tie then. But so one problem is this removing, because removing from an array is a linear operation. So with that length, we'll get n square and run out of time quickly. So that's one place where a heap could help us. Yeah, but we need to find a way how to like process this. There is only from two ants, and there is one other thing. We can't like change the order of this initial array, because if we sort them, these values, yeah, because we need this order needs to keep. We are reading them in this order. That's the thing. Yeah, because we are reading them in this order. Because somewhere it says from the first bench or the last bench. Okay, so from the start or from the end. So we need that order, that queue we need to continue that few. But as we read from the ends, we want to prioritize those smaller values. So total cost to hire key workers and yeah, like in this first case, this example, we can take the this 17, 12, 10, 2, 7, 2, 2, 7, 2, 11, 28, 11, 28. So in this one, the thing is we will be reading it from both sides. So so we're starting with my pencil with 2. Starting with 2 ends. So we'll go like this 4 first. And these 4. And so we need to pick these 2. Then we need to pick their index, smaller index. And I mean, the logic is now I kind of understand the logic, but we cannot do like full simulation. Full simulation because it has multiple problems. One of them is reading these sides for each k. That's already like if you want to read the full, it could be like pretty much the full length up to the bench length. This candidates could be both of them is up to the length and k time. So you need to read the full thing. Then you need to, so for each hire, which also could be up to the length, to read it, and then you need to remove the candidate from that list, and that is another that's another, removing is another operation that could be linear. So two linear operations, both of them we should use a heap for, and for both of them, yeah. So by the way, why don't we use the heaps? Yeah. Why don't we just create two heaps? A left heap. We can't even. And right heap. And they will fill them up with the data from the bench. In the hiring session, yeah, we'll get the data. Yeah, so when we remove the hire, that means we just take the next, put that in the bench. Yeah, we don't really worry. Yeah, we just add that next to that. Yeah, so I guess that's the solution. Yeah. Yeah, well, at least in about 30 minutes we got the logic. Can we do it without using a heap? I don't think so, because the costs is pretty lengthy. So using the range of the cost, using a count sort, using count sort would would require again this linear time, because even if you have like 4 values, you need to check the entire range. Yeah, so it's a heap thing. Well, it turns out that the standard library of Go has the implementation of the main heap, and I think that's what we're going to use again. Yeah, because we need it. We need it here. Yeah, so I'll just copy it here. So we're going to import. I don't know if we need to explicitly import this. Probably we might not, but we'll just have it. So we don't need to do it with font. Yeah. And okay, so we have the type. So this class, as you call them, so there is this type, and with the methods, these are needed to use to use the heap implementation and match the heap interface. This is int heap is a min heap events. So if we have all these methods, we match the heap interface, and we can then create these objects. So yeah, we'll need the left heap. Left heap is, we'll create it, is int heap typically they this creates the pointer as a pointer type, so that the methods could be called, because these push and pop, they are used on the pointer types. Yeah. So again, yeah, we'll have this. Yeah, because the receiver is a pointer here. Okay, we have two heaps, and we'll be filling them up. We can't fill them up initially. Probably want to do that. And then we'll be moving the pointer, filling them up one value at a time at a hiring session. So let's fill them up initially. They are actually going to be a slice of costs. So inside of that, we're gonna put, because the type is essentially a slice. Yeah, we'll have the costs. And we will need candidates +1. I think this should be like that. Otherwise, we could just say, okay, this left heap on the second line. Yeah, we could just costs, but yeah, we can just put the data, like, let's say that this, I don't know if you actually can do that, because they're different types. The int heap does, the int heap is the type int heap is of slice type. So I wonder if we can actually just assign, like if we can actually just say that left heap, which will be a pointer. So we will need to dereference left heap is now this. So I wonder if that's gonna work or not. I'm not sure. I don't know, but it could. It might. Yeah, we push the pop so onto the hip. So yeah, okay. So this is how it did it. It puts it. They put the values like that, and just just the constants directly here. So I guess we can do that. Or just do that, because that will that should work. We'll see. We'll see. I think, yeah, those should work. Here we'll start from length of cost. So this length of cost, if it's like 10, the last is 9. Minus candidates. Minus candidates. So will that work? Because what we have is, let's say if there's length is 10, so index is last index is 9, and we want to have last 5. That means we need index 6, 4, 5, 6, 7, 8, 9. So we need to start from this index 5, essentially. So if we say 10 minus 5, that will give us 5. Yeah, so this should work. Right. Okay, we have the data for the hips. Now we need to initialize them. Hip init. Hip init. Left hip. I don't know if I should put it hip init right hip. Should we call them like something L hip, R hip? Will it be better? Oops. To call them something shorter a bit. A bit shorter. Well, we initiated them and we are ready to use them. We are ready. We are ready to use them. A little break. a little break. So basically we need to do k times, for range k, which is, a loop that will run k times. What we'll need to track is we'll need the total cost, right? Return the total cost. I'm always confused if I should name result is 0, return int 64 of result. And now, well, we need two values at the top of the heaps, and we'll pop the one that's on the left if they're equal. So as we assume, the one at the top you can get like that, because the array, you dereference, so L heap and R heap. Depends on how they play out. We need the min, Well, if the right one, essentially, if the right one is bigger, smaller, essentially, if the right one if the right one is smaller or bigger than the left one, then we use the right one. One problem here, as they have mentioned at some point here, notice they go like, notice that the worker with the index 3 was common in the first and the last. So right and left is very helpful only until both of them start getting into the same benches. Until we get, once the benches overlap. Well, how do we do that? When the bench starts overlapping, it essentially has it will be in both left and right. So so we need to handle that somehow. Yeah, so how do we handle the situation? Is we wanted to just, oh, it becomes just one, essentially it becomes one heap. Once they overlap, it becomes one heap, but we need to look at, we need to look even on, here is the thing. The rule for less. Yeah, we let go of the index, but when we have, when one, I think that will be this logic will not move values, will not change the order of values that are equal. So this is kind of the sorting, I think that's the sorting, part of the sorting logic. And that they use. And if the values are equal, the order will be the same. So we will get the smallest index, I think. In our algorithm, in our part of this thing, we just want to stick to the left. Yeah, only use the right when it's actually smaller. If the right is smaller, then we will use right. Then we will pop from the right. And by the way, I mean, popping from the hip is one thing. But well, essentially that just means we need to add one more value from the, to the right. Right? I mean, because what happens in that heap stays within that heap. So it just says we need one more value to add to that heap because of, its length is smaller. Yeah, so basically the value that's, if right is smaller, then we pop the value from the heap. Yeah, we say heap pop r heap, and we don't need to pass it the pointer pop, and that value will be added to result plus we add to the result. And now we need to we'll need two pointers, I think left and right, which once they touch, we essentially Well, now we need to think that logic through. Yeah, what happens? There are two milestones. When they touch, when they're next to each other, it doesn't matter. Yeah, but when they start overlapping, that's the thing. Yeah, when the left is equal to right, what happens then? Yeah. So essentially, we're good with that. Else, we add to the result if they're equal or the left is smaller, the left one wins because it has the smaller indices. Yeah. Okay. A little stretch. My dear viewers. So, yeah, so we need to take care of those situations. It's two situations. Because this is good with getting us those lower cost hires. Now we just need to feed the data from costs. We can do it in a separate, like if the right hip length I'm trying to think if it's kind of easy here. Yeah, we know we read from the right hip, so now let's see what we need to do. And let's look at the two scenarios. If they're actually close to each other now, like left and right. Hold on, I need to. Close that second door. It's kind of noisy in the game room. And okay. I mean, the general case, well, it's not really general. They could be like, the benches could be, the benches could be pretty long from the get-go. But let's say they're very short, so we would need just to have some pointer at pointer, the right pointer will need to move, and we will need to push onto the hip push. And by the way, this function, as we know, returns, when the pop returns any. So we need to assert it's an integer. insert an integer. Yeah. Because when it returns, it will not return an integer. Okay, and the same thing here. And I mean, so then we'll push again. The push also works on, so just push on the right heap. We'll push to the right heap what? Yeah, the push method takes the push takes the heap and the value. Yeah, the heap and the value in costs at index R. Yeah. Same thing here. And that's the general case for the left one. Left. We do need those left and right. Keep the track of these two. 0 and length of costs -1, because that's the last index. We are approaching 1 hour. We are at 1 hour. Hopefully we'll finish this soon. So that should work. The priority here is given to the left heap. And by the way, do we really need 2 heaps? If we add the values, oh, here is the thing. I mean, if we just add them to 1 heap, then adding the right one after the left one. Adding the right one after the left one. Maybe that's enough. Maybe that's what we need. We'll just have 2 pointers. No, we'll just use, we'll add the left one, then the right ones. Oh, wait a second. We need to know if we will not know. Yeah, where they came from, so we will not know where to take them from. Yeah, I think because if we just put them all in one pile, one heap, Yeah, we take one. Where do we fit the next one? We don't know. So yeah, that's why we need to. Yeah, but the priority, yeah, the right one only wins when it's actually smaller, when the value in the right one is actually smaller. Once they start overlapping, they will have the same values. And the more they overlap, the more, yeah, so if they have the same values, the left always wins. Yeah, so I think this should work. And the left one will be just taking, taking the data, but now we don't want the right and the left to go like too far. And we might have less, we might have a situation where there is less candidates now. So there is, where we still have candidates on the benches, but we ran out of so they are all on the benches essentially. Yeah. So we don't want to try to read after. Yeah, only if there is more to add, then add. Yeah. Yeah. Yeah, if R, yeah, so this reading, if R is bigger than 0, actually we will probably stop the R earlier, but it should work. We don't need to go, with the R further than left, essentially, because the right one, if it had like all the smaller, but then it reaches the left one. By the way, they might overlap right from the get-go. Like, I think it was they might overlap just immediately. And the left one will have the priority. So the right one, well, we definitely don't want it to go below 0. So, and left one, if left one is smaller than length of costs minus 1, yes, then we can read more. Yeah. I don't know if we need to read into the on the left side. The left side should read. Like, the question is, do they need, when they actually start overlapping, what should be the rule? Like in this case, notice that workers with index 1 are common in the first and last 3 workers. So the common ones, those overlapping, they obviously fall onto the left one, so they are priority. So I don't know if we need to put them in the right one, but I don't think it's gonna hurt. if we do. So do we need to do anything else? So, and yeah, so we're adding these values to the result, and we're putting them into our priority queues. And this might be enough. Let's see. Let's try to see all the bugs. Composition literal. Yeah, so this is the literal. Possibly missing comma, or so we want the values. These initial values to be in our heap. Possibly. So it doesn't want to put them there. Well, let's then put them. Let's try the other way. That shouldn't work, but we'll try it. He's okay with that, so. Oh, wait a second. Cost isn't valid. Yeah, oh, by the way, we forgot to use this operator, the 3 dots. The 3 dots, which has a name, which essentially populates, wait a second, undefined cost, length of costs. If so we did assign them to them, but there is no. Oh, wait a second. Cannot index our variable of type, not index pointer to heap. Our heap variable of type pointer. And that's exactly what what's been done here. I don't understand. What's your problem? Okay, so it needed these parentheses. All right, so we have a little miscalculation. We got it right in the first one. Second test case, 3 instead of 4. Yeah, 3 instead of 4. So, well, we could like, for time's sake, just see what result we are getting at each loop. 1, 2, 3. We were supposed to have 1, 2, 1, 1, and then another 2, but it becomes 3. It reads 3 instead of. So that could be the problem. Okay, so this case is 1, and then another 1 on the right. So the right moves on to this one, yeah. So the right reads the values that were already consumed, yeah. These values, we don't want to move the right to the values that were already consumed by the left. So essentially, we want to keep the right out of its, yeah. If right is more than left, no, we don't even want to add. The same thing for left. So how do we do that? But that could happen from the get-go. They both could just overlap from the get-go. So we only want to get the values that are not already consumed. They have not been already consumed. So essentially, we want the pointers to move and feed the values until they meet. Yeah, so consumption should follow that logic. Yeah, sourcing them from the costs. That's what I think. We don't even want to have them, because otherwise, yeah, this right one we'll just have duplicates, and right one will like say, okay, I have a smaller value. No, it was already in the left value. So that shouldn't be done like that initially. Because we might have the situation of full overlap from the get-go, because the candidates could be just at the length of the full length, and in that case we need to move. So this yeah, so when we want to initialize them, not like that. Yeah, we don't want to initialize them like that. we want to go up to candidates, but also for, yeah, yeah, for L, those left ones, for L bigger than right, and yeah, within L is less than candidates. So if L is 3, it's on the fourth. On the fourth candidates index, fourth index from the beginning, so we're good. But if L is 4, that's too much. So we want them to move whichever happens first. And R is that distance is bigger than the length of costs minus candidates. That will be like 10 minus 10, that's 5. 10 minus 5 is 5. So at fifth, I don't know if we need to do that because we are going to move both of them. We're going to say like L plus plus R minus minus. So yeah, but this one, it should reach 5. Like if we have 10 elements, which is index 9, index 9, so length 10 minus 5 is 5. 5. With index 9, 1, 2, 3, 4, 5. We do want to include 5. So length 10 minus bigger or equal. Yeah, essentially it's like that. And yeah, these pointers will be moving towards each other. We are, and we'll be reading data from by the way, we could say they're not going to be longer than the cost of length. So, but they could be. We don't want them to overlap. So the maximum is probably going to be whatever is smaller, half, we can make them length 0, but capacity we want them for them is limited with either half of the costs. If what if it's odd? The number is odd. We'll add go and by the way, at the next step we will lose. So left should have by the way, if they overlap from the get-go, doesn't that mean that the left has it all? They're just, all of them are on the left. All right, so because, look, if they're longer and they are overlapping, they call this, they are common. Essentially, that means they should be just on the left one. They shouldn't be, they could be equally, like we'll put half on the left one, half on the right one. It will still work because so both should work. But if the number of values is not, like in this case, is not even, then the 7 will stay, will not catch the 7, will miss the 7. And we need to get the 7. But like if their candidates was 5, okay, so 7 would be a common candidate, which what that means is 7 doesn't need to worry about secondary priority. It has its own, it's in the left. That's what it's important. So it's in the left, and I think we should just let left gather everything it can, and then go let the right take the remainder. Because if everything is in the left, that's all we need. Yeah. So I would say let's simplify. Yeah, let's have left get everything it wants. To do that, we could we don't need to even run a loop. We could say that, we could come back to the left, L heap is the full slice of whatever it has of costs. Yeah. The candidates we need to add one? I don't remember. Yeah, if it's 5, there are 5 candidates. 5 is not going to be included. Oh, it's just going to be 4. But index 4, if we put 5, yeah, that's what we need. Yeah. So yeah, left is good. Now we need to give the right whatever is left after that. So if we take the so its portion is this. Whatever is higher, essentially. Yeah, if that is higher, if that thing, if that position, so let's say, because that position could be or just candidates. Like that is the 5th. That is 5. Well, if it's 10 and that's 5, then both it's gonna be 5 for both. If it's by the way, we need to remember that, yeah, because our our left pointer that's the position of our left pointer. Yeah, so left is at candidates 5. And initially +1 because we already took all the candidates. Actually, that might be the last one, so we don't want to move them first. Yeah, we want to take the candidates. Left is not going to be at 0. Definitely not at 0. Well, it's already not at 0. Yeah, so now we just need to, we're at 130. Yeah, this pointer's the right way. So we gave, the left heap got all its costs. That's good. Now we need to give the right hip whatever is bigger. Yeah, if the candidates is bigger, but we don't want to start at candidates because the right one needs to be at least, So that's where the left was. Now, the right is going to be but not the candidates, because we can't overlap on the candidates. Oh, that's not going to be the right. So candidates plus 1, because though we need to check if it's within the boundaries. So candidates plus 1 could be just out of the boundaries. This will, like, if it's like 10 minus 10, this will give us 0, the first candidate. But we don't need the first candidate. Oh, wait a second. No, the R would be at the first candidate. That's good. Yeah. Although we don't need any. That's what I meant. Because it will be like all candidates will go to the left. So I just need to figure that out. There are several cases. If right is yeah, we need to give the remainder of, it's either that which is within the range, but that, if that is bigger, then we need to use that. But that thing could be out of the range. So this could be like 10 plus 1, so that's 11. Now, if we cut, if we slice costs by that, at 11, we might jump out of range. We might not. Let me see if we create an, if we create an array, slice, of integers of length 3, and then we create a slice that takes, wait a second. Yeah, so in this case, our length is, yeah, length is, if candidate equals the length of cost, so it's like 10 minus, this will be 11. And by the way, index 10 already doesn't exist. So index 11 will go out of range. At length 3, yeah, index 3, with 3, B. I think with 3 will be fine. Expected, what is that? Wait a second. Slice A. Oh yeah. Yeah, well, 3 we're fine, but if we take a bigger number, bounds out of range. Yeah, so that plus 1 will bound out of range. So I think we're good because look, if it's 5, 5 will not be included. Like if it's 10 and the index at 5, at index 5, which will not be included, yeah, index 4 will be included. Index 4 is the 5th one. So starting with the index 5 is fine. It will be bigger than that. So it will not include. Good. Gee whiz. So yeah, we should be fine. So we should yeah, we could say this is L and right hip is cost. Yeah, so like that. Now, these are the ends. And after that move, so now we gave them everything. Now we need to start our, yeah, we can continue. We can start getting those. Yeah, we initialized, yeah. Essentially, we initialized our hips. Now we can start using them. And we initialize the pointer, so, oops. And now, so essentially, what will be happening? Both will be moving, but still the priority, yeah, but only as long as they are like not overlapping. It will give the priority to the left. Now, left will have the priority in terms of reading, but we will stop reading. We'll only read if right we will not overlap on either of them, essentially. Yeah. We do want to continue taking the values from the hips, but we will stop reading sourcing data from, yeah, once we read everything, once we read everything. So k times, we need to get our low cost hires. And but getting them from the cost, yeah, if they come from the right, we're fine. But do we want to add to the right? It will depend on if the right is bigger than I mean, the right has to be not just bigger, it has to be at a distance +1. Yeah. Has to be bigger than L. And before we make it smaller, before we move it and take something. So if there is something to take, then we move right, and then we feed the right. If there is still distance, that essentially is if right minus left is more. So if it's like 3 and 4, so right is bigger, but if it's just one difference, we don't want to. Yeah, we can't read anymore. And that's the same thing the same here. Yeah, if the distance is, yeah, will they run out of bound? Because the right, they might run out of bound. Oh, wait a second. Heap mean. Oh, we tried to we started to initializing the heap, the length of the heap, but then we realized we cannot do that. Yeah, so yeah, index oh, index out of range with length 0. Oh, what if yeah, the right could be empty. Oh, it looks like the heap was empty. One, two. The second case. Yeah, because the left took all the key, the left, and then the right was empty. So we don't want to read that. We only want to do that if the heap is. So if we need first we need to check if the length of it. If yeah, by the way, it has the method length. Yeah, we have the method length. Need to just call the method length. Yeah. So this triggers if right is longer. Oh, it's smaller. If what's on top of right is smaller. But before we check that, we need to make sure there's something. We need to make sure that this R hip length, and they just call it like that, yeah. That R hip length is not 0. Yeah. Yeah, so if it's not 0, because if it's 0, we just go look at the left one. We just pop the left one. But what if the left one is empty? What if we filled up the left one? It's all gone. Essentially, the one that's empty if right is empty, we just go to the left one. If left one is empty, yeah, if right one is empty, we don't need to, yeah, we don't need to do even this comparison. If right one is empty, we're done with the right one. We try to read from the left one, but we need to make sure no, this should happen. No, this is the case that right is not empty, right, and the value on the right is smaller. But I need to check that left is not empty. Yeah. And left heap length is not nil. Oh, it's not. Yeah. So that's one case. They're both are not empty. And the right wins. The other case is if if the right one is empty, we just go. And that will be triggered here. Yeah, if the right one is empty, we'll automatically look at the left one. What if the left one is empty? We need to look at the right one. So that's one case. Or another case is, yeah, if the right one is not empty, Okay. There should be a situation when both are empty. Yeah, we're not gonna get that. But one of them can become empty at some point. So that case should be triggered in several situations. And one of them is if left or if left is empty, yeah, if left one is empty, right is smaller, or right is the only one with values, then we take from the right. Okay. And otherwise, if left is smaller or how do we treat, where is the case when right is empty? If right is empty, if right is empty, this will not happen, or should not be happening. Yeah, right is empty. Yeah, so I think it's like that. Okay, that one works. The first one is a bit off. Oh, it adds 7, but it added something else. Instead of 7, it looks like, so it was supposed to add 2 to 7. Yeah. Lowest is 2. Lowest is 2. Lowest is 7. But instead, it added 8. 2. Oh, it looks like it never got into 7. It looks like it never got into 7. Yeah, it should take like 2, then left 1 should push the value from the cost. Should get the 7. Okay, if right minus, I wonder what they are, because oh, they're 5-4 from the get-go. They're like 5 and 4. Left is 5. Oh, wait a second. Right is 5, left is 4. Yeah, but they're already on each other from the get-go instead of being at a distance. 1, 2, 3, 4. So 1, 2, 3. There should be 3, 4, 5. So there should be 3, 5, not 4, 5. Oh, wait a second. No, at the first print, left should become 4. So 7 should be there. 7 should be there. Well, print me the left heap. I want to see what it looks like. And print me the right heap. 10, 12, 17. So after taking 2, yeah, so it didn't add 7. Didn't push 7 on the, oh, jeez. Why is it pushing on the left? On the, yeah, it's, wait a second. Left heap should receive, yeah, in this case, yeah, we are pushing onto the right heap. And in this case, we're pushing on the left heap. At 1, 0, 1, 2, 3, 4. At 4, which is where left ended up. Heap, left heap should have the 7. So 2 hours into this, just essentially working through the pointers, handling the pointers. So now for some reason, left heap, why is it not having the 7? It just has 17, 10, 12, 17. But it never gets the 7. But it moves. It moves it. Yeah, L and R. It does move. The left pointer is at 4. But what if it, it might have been initial at 4. Wait a second. Left is candidates. Candidates is 4. That's why it says 4, yeah. Yeah, so it's a bug. Left should be at 3. Left should be at 3. So left pointer should be at candidates -1. but this should be at candidates because, or we should be say like +1. Right. Right should be where it is. I mean, we definitely want to like refactor these pointers. Okay, use test case. Yeah, so it gets, oh no. Read that test case. Thousands of values. So this is kind of you know what? I think it's 2 hours. We should take a break. And that's kind of a good example of a problem where you have all these pointers interplaying, and it's a good practice to get comfortable with them. Yeah. So this is definitely the type where should be more practice. Get it within an hour, and then within 30 minutes. Anyways, thank you for watching, and we'll see you in the next videos.